After we are done with your lines, okay, relationship between two lines, we are going to talk about intersections between line and a plane. Okay, under this relationship, interaction between line and plane, there are a few scenarios again. Okay, if the line is not parallel to the plane, okay, if the line is not parallel to the plane, 100% for sure, the line and plane will intersect at a point. Okay, so you must always imagine lines as never-ending lines and planes as never-ending planes. So as long as they're not parallel, for sure they will intersect some point somewhere in space at a point. Okay, next, if the line and the plane is parallel, 100% for sure there is no intersection under this scenario. Okay, and then if the line is parallel to the plane, there is a possibility that the line is actually lying on the plane. Okay, so these are the main three scenarios between a line and plane. So how to solve for this? If there is any intersection, how to check for or solve for intersection is again to equate them together. So a numerical example will actually run through the key features again. Equation of the line given in vector equation form. Equation of a plane given in Cartesian equation form. Question tell you they intersect. So find for me the points of intersection. So your theory is that you need to equate together. But you look at the equation that you have. This is vector equation. This is Cartesian equation. How to equate? One is in terms of r. One is in terms of x, y, z. There is no way that you can equate directly. So I need to do some manipulation. So I need to rewrite the equation of the plane. Okay, remember the plane is given in Cartesian form. So Cartesian form, switch back into your r dot n form. Okay, this is the r dot n form of your equation of a plane. This is your vector equation of the plane, of the line. I have r here, I have r here. So what you need to do, equate. How to equate? Put this r into this r. And then this is what you actually get. Then of course your dot product better be good. Activate your distributive law. You'll be able to generate one simultaneous equation involving one unknown, and then you can solve for your t to be -2. And with this t value, pump back into this original equation, and you actually get the point of intersection between the line and the plane. So next example is I have point A and B given, and this other position vector that they give it to you. So your job now is to find for me the point of intersection where the line AB meets the xy plane. So this is an intersection between a line and a plane. So of course I will need the equation of the line AB first. So again, remember, vector equation of a line look like this: A plus lambda B. Do you have a point? Do you have the direction? Okay, so I need to find the direction, which is AB. Okay, because the line AB surely is in the direction of AB. And then do you have a point? It's either OA or OB. So you can easily write down the vector equation of the line AB. Next, I want this line to intersect with the xy plane. So how does the xy plane look like in r dot n form? So xy plane, who is the normal vector? Z axis is the normal vector, so the normal must be 0, 0, 1. And if it is the xy plane, it must pass through the origin. So right hand side for sure is equal to 0. This is your r dot n form of the equation of the plane. So what you need to do next is to equate together. Equate the equation of the line with the equation of the plane. So put the things together, solve for your s, and what to do with this s value? Put back inside here. You actually get the point of intersection between the line and plane. So sometimes, okay, the lines do not intersect. The line and the plane do not intersect. So when that happens, they can be parallel. So look at this equation now. Okay, you are given the line. Okay, vector equation of the line. you are given plane pi, r dot n equation of the plane. Your job is to show that the line L is parallel to the plane pi. Okay, you need to show that line L is parallel to the plane pi. So diagrammatically, this is that's happening. Line L and the plane pi. Your job is to show for me that they are parallel. So what is the key feature of your plane is your normal vector. If the line is parallel to the plane, the normal vector of the plane must be perpendicular to the direction vector of the line. So what you need to do is to check with your dot product. Direction vector of the line dot with the normal vector of the plane, and answer turns out to be 0. When that happens, you can conclude that the normal vector of the plane is perpendicular to the direction vector of the line, and because of that, the line is parallel to the plane. So the first part of the question is done. So what you need to do next is, question asks you whether the line now lies on the plane. So how to check? So the line is already parallel to the plane. So I'm going to take this point, okay, the 2, 1, minus 1 from the line L, and I'm going to check whether it lies on the plane or not. So how do I check? If this point lies on the plane, this point must satisfy the equation of the plane. So what I'm going to do is to replace this r by 2, 1, minus 1 on the left hand side. So on the left hand side, 2, 1, minus 1, go and dot with minus 1, 0, 1. If you do your dot product, answer is minus 3. Look at the equation of the plane. It is r dot negative 1, 0, 1 equals to 1. My answer is minus 3. It is not equals to 1. So what it means is that 2, 1, minus 1 do not satisfy the equation of the plane. If it does not satisfy the equation of the plane, 2, 1, minus 1 is not on the plane. Okay, so with that, you can finally conclude that the line is parallel to the plane pi, but the line L is not on the plane pi. Okay, example 8 now. You have same thing, equation of the line L, vector equation form. You have equation of the plane in r dot n form. Now the question asks you to show that the line L now lies on the plane pi 1. So how to do that? Okay, so check. Are they? Okay, what I need you to do, okay, there's a few methods. Okay, the first method I'm going to do is take down the equation of the line L, equation of plane pi. Check whether they are parallel or not. How to check? So just like your previous example, I'm going to use the normal vector of the plane. I am going to use the direction vector of the line. I do a dot product. If it's equal to 0, I nicely conclude line L is parallel to the plane pi. Then what I need to do is I take the point from the line and test with the equation of the plane. So dot product happens to be minus 3. So what it means is that this 2, 1, minus 1, which comes from the line L, actually satisfy the equation of the plane. And with that, you can conclude that 2, 1, minus 1 not only lies on the line L, it is also lying on plane pi. So if 2, 1, minus 1 is lying on line L and the plane pi, and at the same time L is parallel to the plane, the entire line L is on the plane pi. This is your first method. If you don't want to do this, what I'm going to do is I'm going to pump the entire equation of the line into the equation of the plane. This is the equation of the line. Okay, r dot. This is the equation of the plane. Okay, negative 1, 0, 1. If I put in r, which is the equation of the line, and it turns out to be minus 3, which is exactly the equation of the plane. Okay, if it turns out to be exactly minus 3, what it means is that this whole line satisfies the equation of the plane. And with that, the entire line surely is on the plane, such that the whole line equation can satisfy the equation of the plane. Okay, one last example. Okay, this example is very theoretical. So you need a bit of understanding in terms of the theory to help you go through this section. So you have line L, vector equation form. You have plane pi given in Cartesian form. Your job now is to find for me P and Q. I give you the condition that the line L is on the plane pi. So just like your previous example, if the line L is on the plane pi, line L must be parallel to the plane pi. And if line L is parallel to the plane pi, the line L must be perpendicular to the normal vector of the plane pi. So direction vector of the line dot with the normal vector of the plane. So this way is not easy to see. Let's write it down. R dot 5 minus 4p equals to q. So from Cartesian form, I write down in your r dot n form. One look, this is the normal vector. So back again, direction vector of the line dot with the normal vector of the plane. And it turns out to be, it's supposed to be 0 since they are supposed to be perpendicular. So from here, I can actually solve and get my p to be equals to 0. Okay, so I found my p. Then, if line L is on the plane pi, this thing, this point on the line L must satisfy this equation, right? So I can either put it back in, put this 30.50 into your Cartesian equation, or I can put 30.5 equals 0 into the r dot n equation, and I can solve for my q value. Okay, that is your method to solve a question like that.